concentration unit of choice for chemists is called molarity, and we define molarity as being the moles of solute per liter of solution. Now, part of our success in dealing with these problems is going to be able to read word problems, and so it would be helpful to know that if we see the word in a mathematics type problem, the word per means to divide. So this is going to be some division, which means that if we wanted to put this in a formula, we'd say that molarity is equal to, on the top we'd put in moles of solute, and in the denominator we'd put in liters of solution. And it's going to be important for us to know here that this here is per amount of solution, not per amount of solvent or anything else. So it is per amount of solution. And as far as the symbols go, we abbreviate molarity with a capital M. We abbreviate moles with MOL, and we abbreviate liters with an L. So in symbols, it looks like this. Big M is equal to moles over liters. And then when we encounter it, if we want to read what it stands for, if we see 1M, and you've seen this when you've gone in and done your lab activities and seen chemicals that have been prepared for you, we state this as being a 1 molar solution. And then we would label it as 1 mole over liters. So then if we see a label that reads like this and you encounter it in the lab, and we want to know what this stands for, this would stand for 6 moles of NaOH per liter of solution. So then what we're going to do is we're going to do some calculations, and the first calculation would look like this. What is the molarity of 2.00 liters of solution that contains 32.0 grams of sodium bicarbonate? When we read this problem, first of all, we ask ourselves what it is we're looking for. In this case, we're looking for molarity. So I come back to our formula, which says that molarity is equal to moles over liters. And then as we read through the information in this problem, we try to see, do we have the number of moles in here? We don't. But what do we have between these that could easily be converted to moles? We have grams, right. So we can easily convert grams to moles. Do we have the number of liters in here?
Yes.
Yes, we do. So we have the number of liters, which we could actually put in right now. We can put the 2.00 liters in the bottom. We don't have the number of moles, but we can easily get that out of the 32.0 grams. So we'll start with the 32.0 grams of sodium bicarbonate. We want to convert this to moles of sodium bicarbonate. And then we need to remember, how do we convert from grams to moles? What are we going to need?
Molar mass.
Right, we need the molar mass. And the molar mass we calculate from where? Periodic table. So we pull out the periodic table and we calculate that molar mass. We need the sodium, we need hydrogen, we need a carbon, we need one of each of these, and then we need how many oxygens? 3 of those. So we add up those atomic masses. Let's go ahead and do that. Once we add all of those up, we wind up with
84.01.
84.01, right. So then we come back here and we ask ourselves, where do we put in that 84.01? Goes in the bottom. And the units on that are grams of sodium bicarbonate. And on the top we put in 1 mole. of sodium bicarbonate. So at this point, grams of the sodium bicarbonate cancel out. We then go to our calculators and we calculate 32 over 84.01. And we'll carry along an extra digit at least for right now. We come up with 0.3809. It looks like we should really only need 3 significant figures. So we come back here at the 0.03809 moles of sodium carbonate. We divide that by 2. And once we divide our answer by 2, how many significant figures should be in the answer? 3. So we round this out to 0.190. And the label on this is moles of, it's not NaOH, it's NaHCO3, NaHCO3 per liter. But then we remember, what does 1 mole per liter stand for? What do we replace moles per liter with? Big M, right there, exactly. We replace it with the big M, and we then say that the concentration is 0.190 molar sodium bicarbonate. So, any questions on this calculation here? Any questions on the calculations? All right, next up, let's look at this one. What mass of sodium bicarbonate is needed to prepare 250.0 milliliters of 0.200 molar sodium bicarbonate? And then the follow-up question will be, describe how the solution would be prepared. Now, when you read through this one, we do have some hints here. We do see 2 quantities separated by the word of. And again, when you read through these, it should help for you to analyze words. If we see 2 quantities separated by the word of, what does that mean we need to do mathematically?
Multiply them.
We need to multiply them, exactly. So we come back here and start off with this calculation. We have 250.0 milliliters of 0.200 molar sodium bicarbonate. Now the problem with writing it like this is we don't see any units here that can cancel out. So we need to look at it a little further and remember a few things. First of all, in this one here, we see that we have big M. And remember that big M, we can substitute big M with which units? Moles over liters. So again, big M, we're substituting in moles per liter. And we do that to help cancel out units. Except we still can't cancel out because this is milliliters, this here is liters, which means then we need to take the milliliters and convert this into units of liters. So if we want to convert that into units of liters, we take the 250 milliliters and we want to convert this into units of liters. And so to convert this into units of liters, we need to remember that for every 1 liter, we have 1,000 milliliters. And so milliliters are going to cancel out, and that's going to give us 0.2500 liters. And that then is what we can put up here, the 0.2500 liters. Well, now once we've done that, we should be set up to solve this problem. So to solve it now, liters are going to cancel out. And once liters cancel out, we have units of moles. But of course now we're not looking for moles, we're looking for mass. And mass is measured in units of grams. So if we want to know the mass, we want to figure out how many grams that would be. So if we want to convert this over to grams, on the bottom we are going to put 1 mole of sodium bicarbonate. And on the top we're going to put 84.01 grams of sodium bicarbonate. And so see, we already calculated that molar mass up here. There's 84.01 grams of sodium bicarbonate in every 1 mole. What happens then is that moles of sodium bicarbonate cancel out. Well, now this is set up to solve this problem. We then take 0.2500, multiply it by 0.2, and multiply it again by 84.01. Once we get that answer, how many significant figures should be in the answer? Should be 3. So we round this out to 4.20 grams of sodium bicarbonate. And that then is the answer. So that's part A. Any questions on part A? Any questions on part A? Part B. We now want to describe how the solution would be prepared. So in other words, I know I don't have you in lab, but you are going to be doing these in lab this week, whether you have lab tomorrow or whether you have lab Thursday. The good part about it is you're going to have to pay a lot of attention to that lab, because a lot of what's on that lab is what we're doing right here, and you're going to see it again in your lab, and then we have the test. Some of you will have that test right after your lab, then on Thursday. So, as we look at these devices up here, you've worked with these already. What are these things called? Graduated cylinders. So have you worked with these? You haven't worked with these yet, but I have a number of these out here, and these devices here are called volumetric flasks. And you have worked with some of these, but you'll be working with these in lab tomorrow. These here are called pipettes. So of all these devices up here, which device do you think would be most useful in making one of these solutions? Graduated cylinder, volumetric flask, or the pipettes? Actually, I could pick either the graduated cylinder or the volumetric flask. When possible, if we have the right size volumetric flask, we pick a volumetric flask. And the size we pick would be what size? Well, how much solution do we want to make? 250 milliliters. So if we want to make 250 milliliters, we're going to pick out one of these 250 milliliter volumetric flasks. Then, if we want to make the solution, we're going to make it in here. So how much water should we put in? Or is that where we should start? Where do you think we should start with this one? Any ideas? We want to make the solution in here. How much water? Any idea?
Half of that ball or
Okay.
up to the line.
Yeah, it's up to the line. There's one line on here. Okay, and that one line measures 250 milliliters. Well, here's how we're going to do it. The first thing you have to do, you have to actually measure out the sodium bicarbonate. So this one I know we darn well better get. How much sodium bicarbonate are we going to need? 4.20 grams. And how are we going to measure that out? How do we measure 4.20 grams?
By weighing it.
By weighing it. On what? scale or a balance? Sure. So we're going to we'll weigh out 4.20 grams of sodium bicarbonate on a scale or balance. And then what are we going to need to do with that? Put it into the volumetric flask. Okay? Then once you put it in here, then what are we going to do?
Add the water.
Add water. Now here's kind of the trick. The water that we're going to add in here, we don't want to fill it all the way up to the line just yet. What we'll do is we'll probably fill it about half to 2/3 full. We put enough water there to get it all mixed up and swirl it to dissolve. And then once it's all dissolved, then we add it up to the line. And remember that this is going to be a curved surface, so the meniscus should be on the bottom. And so we measure the bottom of the meniscus right on that line. Once we add water to that line, then we mix it thoroughly. And once we mix it thoroughly, we have the solution. So let's write out those instructions. Once again, we are going to measure out 4.20 grams of sodium bicarbonate on scale or balance. Add the sodium bicarbonate to 250 milliliter volumetric flask. Then we're going to add water to the flask and mix to dissolve. And once we add water and mix it to dissolve, then remember we need to do what? Add
Water until it gets to the line.
water to the line. We're not quite done yet. Then what are we going to do? We can't just put the water in there. Once we put the water in, then we have to
Mix thoroughly.
mix it thoroughly again. Now the reason why we add the water into 2 steps would be for something like this. Let's say that what we wanted to do is we want to make a mixture of sand and marbles. We're going to mix together sand and marbles. So let's say I put in 100 milliliters of marbles, and I pour 100 milliliters of marbles into a container, and then I put 100 milliliters of sand and pour that into the same container. Now we have a mixture. So 100 milliliters of marbles, 100 milliliters of sand. What is the volume I'm going to have once I mix those two together?
200.
I'm not going to have 200. It's going to be, it's not going to be 100. It's going to be somewhere between 100 and 200. And why isn't it going to be 200? Why can't it be 200?
Because the sand will fall between the marbles.
Right, the sand is going to wind up falling between the marbles. And molecules are much the same way. They come at different sizes. Some molecules are really big. Some molecules, like water, are really little. And so what happens very often, because water are really, really little molecules, once you mix them with a solute, and many solutes are big molecules, what happens is that water fills in those spaces between the molecules, and if you add the volumes together, the volume you get at the end is usually less than the volume you start with, simply because you fill in the spaces. So what you do then is that if you want to make 200 milliliters, you have to first add in the sand and the marbles, and then you're going to bring it up to the level with the water in there, or with the sand in there, to bring it up to that total volume, assuming that the marbles, in effect, is the solute. And so we do the same thing here. We add the water and the solute together. We get that solute all to dissolve. So we then, in effect, filled up all of those empty spaces. And then we can bring the water up to that line and get it to be mixed thoroughly. And that's how we make that solution. Now, something else we should do here, if we want to word it more simply, we could simply say we would dissolve 4.20 grams of sodium bicarbonate in enough water to make 250.0 milliliters of solution. And the key here is that we are making 250 milliliters of solution, and we go back to our definition, which again, molarity is based on the amount of solution that's in there. Now, if we would have made it in a graduated cylinder. We could have used a graduated cylinder on this. It's just that we'd add the solid in there, and when we fill up the water could ultimately be filled up to the 250 milliliter mark on that graduated cylinder. So this could be used, but again, given a choice, which one of these is the more precise one? It's going to be the volumetric flask, in part because if you look at the size of the neck, this one here has a nice narrow neck, this one has a kind of a fat neck on it. As a result, then it's a little more difficult to wind up with the more precise and more accurate volume. Now, what's kind of interesting about these is it's very difficult to reproduce these with the same consistency over and over again. So they actually have somebody, when they make these things, their job is actually to scratch or etch lines onto the necks of these flasks. They fill it up with a specified volume of water, and once they fill it up with water, they see where the bottom of that meniscus is, and then they etch a scratch or line around that. And so if you go in the lab tomorrow when you're going to be working with these, you're going to see that some people in your volumetric flasks have lines that are down here. Some of them have lines that are up here, because the ability to reproduce glass consistently on a repeated basis is very suspect. In fact, you'll see when we work with things like the beakers, this one doesn't have it, it says approximate volumes, but many times they'll say on there like plus or minus 5%, simply because in order to get that high level of precision, especially with glass, it's very difficult. Okay, and I'm going to turn this on for a demo coming up here in just a bit. Now, let's say that instead of making 250 milliliters of solution, we had dumped in 250 milliliters of water. So again, we start at 4.20 grams, we add 250 milliliters of water. How much solution do we have at the end?
More than 250 milliliters.
Right, more than 250 milliliters. We don't know what it is. And so this leads to, and this is the rule that I named myself. This is kind of cool. That's because it's called the Kool-Aid rule. All right, it's called the Kool-Aid rule. How many ever made Kool-Aid before? Okay, so if you make Kool-Aid, we're going to do it the real old-fashioned way, and if you don't know what it is, just follow along with us. The way you make Kool-Aid, if you do it the real old-fashioned way, you get a little package of Kool-Aid, you add your sugar, and then you add your water. And so when you add the sugar, you dump in a quart of sugar, you dump in your packet of Kool-Aid, and then you add how much water?
To the line.
That's right, you add it to the line. And that is, you add enough water to make a total of 2 quarts of Kool-Aid. Now, of course, the way my mom used to make it is, she used to measure out 2 quarts of water, then she'd dump in the sugar, and then she'd dump in the Kool-Aid, and at the end, my mom's Kool-Aid tasted how? Kind of watered down, right. And that was because there was too much water in there. If you read the package, and that's why I think of it the Kool-Aid rule, it says on the package it makes 2 quarts of Kool-Aid. So it doesn't say use 2 quarts of water, it says it makes 2 quarts of Kool-Aid. Okay. And that's the Kool-Aid rule. All right, next up. Now, it took a college degree for me to tell my mom that she's been doing it wrong all these years, but, you know. All right, next up. Let's say that we work with our molarity formula and we need to find the number of liters. So molarity is equal to moles over liters. If we want to solve this equation for liters, how do we do it? Well, we need to get it up in the numerator. To get it up in the numerator, that means we multiply each side by liters. Once we multiply each side by liters, liters cancels out. And then we have to take each side and divide it by
Molarity.
the molarity. Good. Once we divide it by molarity, we then find out that liters is equal to moles divided by molarity. So you will have there's a worksheet that if you came in late that was sitting out here, we're not going to probably have time to work on this today, but you'll see that there's one in here where you'll also be calculating the volume, and there's some homework assignments, Master Chemistry, that you'll be working on those as well. And if you find yourself a little algebra challenged, you might remember that when we started this semester, we had the density pi. Well, it turns out that we also have the molarity pi as well. In the molarity pi, we put moles up above, and we put molarity in liters down below. And then if we want to calculate any one of these things, for example, if we want to find the molarity, we cover it up. It tells us we take moles divided by liters. If we want to find the liters, we cover that up. That tells us we take moles divided by molarity, like we have there. If we want to find the number of moles, it tells us we take molarity times the number of liters. So the molarity pi works well for these. Okay, and that takes us through molarity calculations. Any questions on molarity calculations?